Okay, so the first lesson had to do with energy, and the next, I think we have a total of 10 lessons, all have to do with that. Um, and the main concept here is the law of conservation of energy, which you guys all know. And so the first thing that I want to do is just have you realize that in the real world of chemistry, we don't really talk about the law of conservation of energy. Instead, we call this the first law of thermodynamics. All right, and I just want to introduce that now, because later on in your guys' careers, most likely, for example, in the first year of college, the professor's going to refer to the first law of thermodynamics. They're not going to talk about the law of conservation of energy. So I want you to be aware of that going into this. Now, what does this mean? And if I was to ask you guys, all of you guys can do this. You've had this memorized since through 6th grade for sure. It just means that energy is conserved. Now, and I'm just going to abbreviate. Well, all right, conserved. Now, what does that mean? So for any kind of process or chemical reaction, like if we're talking about melting an ice cube, that would be a process. If we're talking about a chemical reaction, it could be like the reaction between oxygen and hydrogen to make water, just as an example. And if we're melting an ice cube as a physical process, then over here we have the liquid and here we have the solid. For anything that's like this, whether it's a physical process or a chemical reaction, the total energy change, which I'm going to write this way, is always going to be the sum of what's going on with the kinetic energy plus the potential energy. So just to give you an example, if for some reason in a process, let's say the kinetic energy is going down, then there has to be an adjustment somewhere in the potential energy, right, of the total of everything. So if we have the kinetic energy of something going down, the potential energy is going to have to be going up somewhere else. Because otherwise, what's going to happen is this number over here is not going to stay constant, right? This needs to remain constant. So whatever's going on with the kinetic energy and the potential energy, they're in a mutual relationship. If one of them is decreasing, the other one has to be going up, so that the total here for everything is going to stay the same. All right? Now, when we talk about this, and this is going to happen in lesson 2, we in order to understand something like either a chemical reaction or a physical transition, either one of these two things, in order to sort out the energy business, we compartmentalize this. So we're going to define a new term which is called universe. The universe. And it's going to be equal to what we call the system plus the surroundings. Whoops. Now, I know that this is somewhat sophisticated language, but the system, this is going to either be your physical process, which we already, we defined that in lesson 1. So that would be like melting an ice cube, or it's going to be your chemical reaction. And the surroundings is just quite simply going to be everything else. All right, and what we're going to be doing here is paying attention to which direction the energy is going. All right, so like in the ice cube example, in order to melt it, it has to warm up. So for the ice cube, we need to increase its thermal energy, right? That has to go up. And literally the potential energy is somewhere else, which in this, so this would be our system. And literally the potential energy, let me use a different color. In order to melt the ice cube, the potential energy and the surroundings is going to have to go down. And if you think about it, this is not that complicated. In order to melt the ice cube, you have to warm it up. And in order to warm it up, you've got to get the energy from somewhere. So where's it going to come from? It's going to come from the surroundings. That's where it's going to come from. And that energy in the surroundings is going to move into the ice cube. And when we do that, the kinetic energy of the ice cube is going to increase. And the result of that is going to be that the ice cube is going to melt. And that we're going to get this transition here. Now, in order to understand this stuff, we have to be able to diagram things. So let me write this up here one more time. So we have our universe. And it's always going to be equal to the total, the system, plus the surroundings. All right, and on top of that, remember this thing, the total energy, right, is going to be equal to the whatever's going on with the kinetic energy in total plus the potential energy. So these things, this has always got to be constant. That sum has to equalize to the same value. If it doesn't, then we're violating the law of conservation of energy. So how are we going to set problems up? So I'm going to be doing it two ways. One way will be to use circles, where this would be my system. And then the surroundings literally will be everything around that. So we can sort out what's going on with the kinetic energy and the potential energy. So as an example, if this was the ice cube, in order to melt it, the surroundings is going to have to go down in potential energy. And the ice cube is going to have to go up. That would be an example. The other way I'm going to represent it will be using boxes. So here would be my system, whatever it is. It could be a chemical reaction, for example. And then the surroundings is going to be everything that is around that. And this way here, by using pictures, we can keep track of what's going on. All right, now with that, I want to go ahead and close the video. Remember that lesson 2 it dropped very early this morning, so you have the video link at ChemDoctor.org, and that's followed by the quiz link. You have that until Friday at 7 p.m. to get the work done. And so I'm going to go ahead and close the stop recording at this